Okay, so for the last inference example, I gave you some more data here. So competitive maze is set up at a local business. The average completion time is 60 seconds. Each month the maze is changed, but the business says the average is still 60 seconds for the new maze. You suspect this is not true for the new maze this week. You sample the maze by sending in your friends and keeping track of their times in seconds. Create a 95% confidence interval and carry out the hypothesis test to explain your findings. So basically, it's either 60 seconds or it's not. So this is a two-tailed test, essentially, right? Explain if there's an error and what it might be. Explain if there's if and why the confidence interval is in agreement with the hypothesis test. If you remove the outlier, does this change the outcome of the inference? Okay, so I put all the data in here, so we're going to add up all the data. Oops. Add up all the data. Looks like there's 21 of them there, right? So we're going to divide by 21 to get the mean. And then the standard deviation dot sample. And then we'll count the number of values, which is 21, of course. Okay. All right, so if we have a 95% confidence interval, this is going to be t dot inverse 0.975, comma 21 minus 1, right? We're going to 2.08, because again, I think I put this in here. If we have a 95% confidence interval, then each alpha is 0.025 in each side, at least half of alpha, right? So the alpha for the confidence interval is, or significance level, is 0.05, right? Which means from here to here is 975, correct? So you get 2.08 here, and negative 2.08 here, essentially, is what we're going to get. Okay, so the standard error is the standard deviation divided by the square root of the number of samples, right? That's this part of the formula, times t is the margin of error. So t critical, or t alpha divided by 2 times that is the margin of error. So essentially I have the mean minus the margin of error, and the mean plus the margin of error. Okay, whoops, wrong. There we go. That is the number of seconds. Okay, so between 46 and 58 seconds, essentially. So between 46 and 58 seconds, right? Whereas our sample at t0 was the 55.2-ish seconds. That's our picture for a confidence interval. So that is the region we would expect the samples to fall in, essentially. That's why it's a shaded region. Okay, versus the hypothesis test, which we're going to do now. Let's paste in the confidence interval. Okay, so this is our confidence interval here. Okay, so we're 95% sure that the true proportion falls in that range of values, essentially. Okay, so step one. So now we're talking about completion time in the maze in seconds. Either it is 60 seconds or it is not 60 seconds. There is no other possibility, essentially, right? Step two, right? Are they independent? Yeah, they're independent because you're not likely to go twice, right? You're not likely to go twice. Okay, not likely to go twice, right? And you're not going to tell the other person, as we're assumed. And if you try to graph the data, it's generally going to look fairly normal. So if we do graph this data, for example, what happens? We'll go to Insert. We'll make a graph, right? And I think I click the numbers, right? And if I do by we'll just number of bins. We'll choose like, I don't know, 15. So it looks fairly normal, close enough. We do have an outlier over here, which it does ask the question, if I remove it, what happens? The outlier is clearly 93.8. So afterwards, we'll remove 93.8, and we'll see if it changes our outcome. But, is this perfectly normal? No, but it is good enough, so we're not going to care too much about it. So essentially, right, this is what we got for our standard deviation. Our sample mean is 60, and the standard error is this for the standard deviation of the sample mean. So independent and normal, and they're definitely selected randomly, hopefully, all right? So that's good enough there. All right, so step 3 is actually doing it. So the t-stat is the sample minus the population divided by the standard error, okay? Which is a -1, so we're going to do T dot distribution, click on that, comma, degrees of freedom, which is n minus 1, comma, true. Okay, and that is not the p-value. I have to do 2 times this to get the p-value. So let's figure out why. Because if I do my hypothesis test, right, the alpha for the hypothesis test is also 0.05 because it's a two-tailed test. So the hypothesis test and the confidence interval are 0.0205. And we have the same t-values, right? Same t-values, except now t0 is 60 seconds. So we calculated t stat, it's over here, negative 2.63. So I calculated this area. But this area is only half the p-value. The other half of the p-value is over here, so I have to double it to get that, right? So what did I get? 0.0079? Right, 0.0079. So I double that, I get the 0.15 essentially, right? Okay, so go back to here, right? I'm going to get step 3, copy, paste, step 3. Okay, so this is the area that I calculated. I have to double it this time to get the p-value, which is 0.15. So clearly that's a very big 0.15. That's not very big. So what's going to happen? So thus, reject the null hypothesis, because we just said that the alpha is 0.05. That's clearly less than that, correct? So therefore, our sample mean is significant and not likely to occur. There is enough evidence to reject the null hypothesis. It is likely the mean that the time is no longer 60 seconds. The confidence interval and hypothesis test are in agreement because we rejected the null hypothesis, and 60 seconds is not in the confidence interval, right? So we rejected it, and we go back up to here, and look, 60 seconds is clearly on the high side, isn't it? It's up here, correct? So the actual times are showing less than 60 seconds based on what we have here, okay? So if there is an error, it would be a type 1 error because we rejected the null hypothesis, and the 60 seconds no, because we did, and when it might be true, right? Okay, so removing the outlier does or does not change the outcome. Let's see. Okay, so first off, let's look at the, let me get this back here. Okay, let's look at what we got here. In comparison. All right, so the t-stat was a very low value, 2.63. That's what we found, right? That is definitely in the critical region, right? Which means we had to reject, okay? And the 60 is clearly not in here. The 60 is over here. So the true population is, the confidence interval is telling the true population is probably here. And this is saying it's definitely lower than it should be. We found enough evidence, basically, because we're in the critical region, which is enough evidence, essentially, is what we found. Okay? All right, so let's go to the spreadsheet now and remove that outlier. So when we did the graph, we said this one was the outlier, right? So we're going to remove that. Okay, so if we do that, then we're going to change this divided by 20 now. The t-value is now 20. That's still true. The standard error is still this. That's still this. T-stat is still that. The area is still that. And the p-value is still that. So the only thing we had to do was change a couple things to go down to 20 values instead. Oh, wait a minute. This p-value is even lower. So the reality is it actually got better, right? Because this is actually even lower now, isn't it? Okay. So essentially, did it change it? No, it actually hardened our answer for us and made us believe even more. It does not change the outcome. The p-value got much lower. Okay, all right. So always check for outliers. Sometimes it makes a difference, sometimes it doesn't. In this case, it doesn't actually make a difference.